for the Alien Conspiracy Podcast. We are your hosts, Agent ETA,
Agent Ether,
and Agent Anderson. Come along as we examine UFO sightings, conspiracies, and all things strange. You can follow the show on Twitter at AlienConPod. We also have an email address, alienconpod@protonmail.com. We would love to hear from you. And don't forget to check us out on Facebook, Discord, and Reddit. Links in the description. This week's episode, Time Travel. Maybe part one. I don't know. We'll see how it goes. This is one of those topics where there's just so many different things you could go into that we may revisit it in the future. It may require another one, but for now, we'll just stick with this one.
This could be just part one.
Yeah, could be. We'll see how it goes.
Because there was so much I was reading about that I wanted to go over, and yet in the back of my mind, I was like, ooh, 1 hour.
Yeah, because there are two problems. First of all, I think 1 hour is about a good length for a lot of people to listen to a specific topic. More than that, and it kind of gets bogged down a little bit, And second of all, man, it's a lot to edit, So if it goes like an hour and a half, 2 hours, whatever, it becomes difficult to get that done in a timely manner because there's a lot to do.
Slacker.
I know, right? Well, anyways, let's get started with Agent Ether. What do you got for us?
Well, I have something that happened in the past. On June 28th,
spooky.
June 28th, 2009, Stephen Hawking threw a champagne party for time travelers. It was in all the papers, of course, after it had happened, and there were drinks and appetizers. Everything was ready to go, and the catch is that he sent out invitations a year after the party happened. They read something like, "You are cordially invited to a reception for time travelers for Professor Stephen Hawking," and it was held at Cambridge. And he gave the coordinates, like the latitude and longitude, and it included the disclaimer, "No RSVP needed."
Of course not.
Was it to be held? Was it to be held on April 1st?
No, it was to be held on June 28th. And in fact, it was held on June 28th. And Hawking said, "I sat there a long time, but no one came."
Oh, what a
That's a sad story.
I was going to say that does sound like a super sweet party, but
a party of one.
Only if you're a time traveler.
And I came across something from the Giant Freaking Robot blog, and it's a reason why there were no time travelers at his party, besides maybe that time travel is not possible. So some of the reasons why he didn't have any party guests were that the party took place on a different reality timeline. The invitations did not survive long enough for anyone to see in the future. In general, time travelers are just dicks and they didn't want to go to his party. And finally, time travelers can't actually control how they time travel, and so they couldn't attend the party. Or maybe Hawking killed them all to preserve the time-space continuum.
Maybe there was actually like some time travelers that actually showed up, and then he's like, "Oh shit! Well, we're gonna have to kill him." I'm convinced that he had like some kind of like laser array or something like that hidden in his wheelchair. Why wouldn't he? He's Stephen Hawking.
When I was researching time travel, I started to think about just time in general, what time is, how people think about it, and how they've thought about it over time. So initially, like in ancient times, people would track the movement of the sun and the position of the stars to kind of divide time into sections. So sundials were used in Egypt pretty early on. And there were other objects like the meerkat, which was an instrument of knowing that used the movement of the stars relative to the North Pole star to kind of track time. And some cultures used the lunar cycle. But really, it's difficult because how you track time depends on your location and the time of year. And it actually wasn't until 1371 that somebody realized if you had a sundial along the Earth's axis around the equator, then it would create equal shadows with each hour of the day. And then everybody could calibrate their sundials to that sundial. But you still couldn't, have small units of time. So it wasn't until 1660 that you had a pendulum clock, and then you could start dividing time into seconds. And then in 1969, the quartz watch was invented. And this is really interesting. It consists of a crystal of silicon dioxide, and it's shaped like a tuning fork.
So before this, let's say a clock or a wristwatch basically worked by storing energy in a spring and releasing that over time, right?
That is correct. They were spring released.
And then it was like gears and stuff. And
Right.
And then when the quartz watch comes along, that's like a whole leap forward in technology.
Right. And the battery would go ahead and replace that spring. So now it's powered by the battery. And that crystal itself is laser cut, and it resonates at an exact frequency. And that frequency will send an electric pulse when it's counted, and that will drive the motor. So the reason I'm talking about clocks, obviously clocks tell time, but why am I talking about clocks? And it's because I wanted to get to the atomic clock, which came around in 1967. It's just like a quartz clock. It uses pulsating atoms, and it keeps a very accurate time. It uses the resonant frequency of cesium. And it's an international system, and all atomic clocks function very accurately. Over time, they're going to lose 1 second in 100 million years.
Wow.
That's because of how slow, what is it? Euplesium? What was it again?
Cesium. It's not radioactive though. It's not radioactive. It has to do with the way the electrons are jumping into and out of their shells, like up and down the different energy levels, so that they're giving off vibrations, and those vibrations are being counted. So it's not actually radioactive cesium. It's
okay, yeah. Then that's kind of what I was thinking. I was like, is that radioactive or something?
No,
Is that what they're measuring? But yeah,
no,
I didn't know a whole lot about this. That's pretty cool.
It is, and
so it's off like vibration, right?
It is, and if our laws of physics are correct in our frame of reference, this second should be the same for everyone. But the thing that's interesting is when one object is moving at a different speed, especially a very high speed, the atomic clock is not going to move at the same time. So you're going to have to account for that time. And what they do is they actually add time to the atomic clock. I think it's like 38 microseconds a day that they have to adjust it to take into account the fact that when you're moving at different speeds, time actually moves differently.
And I'll get to that in a little bit.
I don't go into a lot of detail about that, actually.
That just warped my fragile little mind.
It gets weird. It gets really weird.
And
yeah, for a layman like myself, it's hard to wrap your head around some of these ideas. It's like, what the hell are you talking about?
Yeah, and for me, I don't understand the why of it, but I know that scientists have proven it. So, I mean, I get the basic concepts. But anyways, I'll get to that later.
Atomic clocks were actually used to image the first black hole. I was really excited when I saw pictures of this. I think it was pretty recently, like within the last year or two. And they used atomic clocks to synchronize the data because it was coming in from the event horizon over a period of time. And they were measuring radio waves from their Event Horizon Telescope, or EHT.
Nice.
Mm-hmm.
So they actually imaged a black hole. Is that what you're saying?
Yeah, well, they imaged, it's not visible light. A lot of times when we're looking at images from space, it's on a different spectrum, and then they're converting it to something that we can see with the human eye.
And also, I'd like to sort of correct you there. They didn't actually image a black hole. They imaged the stuff around the black hole.
Right,
you can't actually,
true.
We don't have the technology to currently image a black hole.
It's still really cool.
Give me a mirror. Let me put it on the ground. I'll show you a black hole.
But it's still pretty exciting, though, because I guess up until very recently, they were not 100% sure that black holes were like a real thing. Like, okay, well, this probably is a black hole, but we're not 100% sure. But now we have a picture of, the stuff around a black hole. So we're pretty sure that it's actually a real thing now.
I don't know. Didn't they track like Hawking radiation from a black hole? Like Hawking predicted that there would be radiation and then they found it. And so that kind of also proves that there are black holes.
Yeah.
Oh, looky who I see.
Oh, it's Agent Kruger.
Agent Kruger.
Agent Kruger.
So I was just talking about atomic clocks and how they were used to image a black hole. And I'm going over like the basic history of time and time travel. So I haven't actually talked about specific ways to time travel or anything. I'm doing more like a history right now.
For sure.
Okay.
Sounds good.
All right. So now that we've talked about time, we can talk about time travel. And I think most people out there think about traveling to the future or the far past, like the distant future or the far past. And time travel has been around, the idea, a long time, even in ancient times, also maybe existing outside of time. In Greek mythology, you have a god of time, Kronos, which I didn't know. And he lives in this eternal heavenly home outside of time. And it was Aristotle who said, what is eternal is circular, and what is circular is eternal. So there's also this idea of things and time being circular in nature instead of linear. Culturally, in the West, the idea is that we live very linearly. And just because we think that doesn't make it true. We don't have to travel forward and backwards in a linear direction, even though that's the simplest way that we can think of time travel. The idea of time travel, as I said, has been around a long time, and there's a lot of different literature and fables and myths. There's one of a Jewish man, Honi, falling asleep beneath a carob sapling, and he awakens 70 years later, and it's bearing fruit. In the Mahabharata, there's a poem about a king who wants to find a husband for the princess, so he travels to the realm of the gods and returns 116 million years later because time has passed differently there. And a lot of times when you're reading about stories, it's like a sleeping thing. Like you get displaced or you fall asleep and you end up in the future. Or there's Connecticut Yankee in King Arthur's Court by Mark Twain, which I've read. It's a really fun story. I read it as a kid. And the character is an engineer. He gets hit in the head, and for some reason, he wakes up in the past. The book itself is actually a social commentary. It's satirical. It's about the Catholic Church and slavery and the triumphs of science over both. But it's also just a good story. It's a fun story. But the idea itself of a time machine wouldn't become popular until H.G. Wells wrote his novel in 1895.
I've read that one. Yep.
Yeah, it's kind of weird. It starts out, I feel like it starts out in a really good place, and it's a lot of fun. And the further on you get into the novel, like the weirder it gets. And then at the end of like, I'm not sure if I liked this or not.
Yeah. Well, it has a strange ending. It
yes.
I didn't see it. It didn't seem very hopeful. I'll just leave it at that. No spoilers.
But the beginning's kind of interesting. There's a dinner party hosted by this time traveler, and he's explaining that time is actually the fourth dimension. And he asks his guests to picture a cube. It's three-dimensional, but it needs to exist in a period of time in order for it to be a cube. If it doesn't exist, if it exists in 0 seconds, there is no cube. And if it exists in at least 1 second of time, there is a cube. So there is a relationship between space and time. And the only difference is the consciousness and how it progresses along the time axis. We ourselves can only travel along the time dimension. Gravity weighs us down in the third dimension, but you can still transverse using this time machine, which I don't think is really explained how he builds this time machine or how it works. But it goes from there. He travels to the future. He describes like the sun streaking across the sky. He stops like every few hours, and then the period of time that he's traveling gets longer and longer until he finally stops 800,000 years in the future in a garden. He comes across these creatures. They're childlike. They live in like a communal setting. He thinks it's like perfect. It's absolutely wonderful. Then he realizes there are two species, and the other one is monkeys, and they're living underground, and there's like a war. And he goes further into the future, and he says all life has died. And finally, he returns home to relate the whole story back to his dinner guests. All right, hold on.
I can hear that, Cryptid.
Yeah, Agent Anderson's taking care of it. Hold on. He's got a case of the zoomies.
Agent Egg got them all riled up.
Did he really?
Zoom.
All right. I'm back.
This is a cryptid break.
Cryptid break again. Yeah. I'm back, you guys.
Yeah.
So the thing about this H.G. Wells story is that he's only traveling in the future. And because he's traveling in the future, we don't have to talk about causality. No laws of physics or logic are being violated. And when you travel back in time, then you can start talking about those sorts of fallacies. One story I really like that's a little more modern is The Time Traveler's Wife, which is also a movie, but the book's way better. And just like there's like genetic abnormalities and you get the X-Men, the main character has a genetic abnormality where he gets bounced about in time. So instead of living chronologically along his own timeline, he has no control, and he's moved to different portions of his life where he has to live them out.
Which story is this?
That's The Time Traveler's Wife.
It sounds an awful lot like, sort of like Slaughterhouse 5 as well.
Really?
Where the protagonist becomes unstuck in time, but that one, the way it's written, it's sort of a little different. Some people see it as a science fiction novel. I did not when I read it, but anyways, please continue.
All right, so we're here in the modern age now, and we have a much greater understanding of science than we did before, specifically how science and time can be defined. And we're seeing a lot more in culture, TV shows, and movies where time gets bent and twisted in new ways. So the question is, are our laws of physics correct? And is our understanding of the universe is correct? Or are we just beginning to realize how things work?
I'm going to go with option B. All right. Let's talk a little bit about said physics. Now, let's start a little bit, just a disclaimer here before I get started. I'm not a physicist, and our resident physicist did not want to actually talk about physics, so she left it up to me. So I'm going to talk about physics. And I'm not a physicist, and I don't claim that everything I'm about to say is absolutely correct. I'm probably going to misstate some things or make some mistakes or whatever. So I'm just doing my best here with, basically talking about some concepts surrounding the idea of, relativity. That would be Einstein's relativity. But let's start with what happened before that, which is Newtonian physics. So one problem that physicists have is they need a frame of reference to measure something, whether it's motion or heat or whatever. You have to measure it against something else. For example, if two trains are moving on parallel tracks at the same speed and direction, they will appear motionless to each other. A passenger would need to look at the surrounding terrain to perceive motion, not at the adjacent train. But what if one train appears to move slightly faster than the other? Is one train standing still? Are they both moving in the same direction at different speeds? Or maybe they're going in opposite directions. You can't tell without looking at the terrain, or the terrain's motion relative to the Earth. And that terrain would be some sort of absolute reference point that you can use to measure the movement of the trains. Now, it gets a little weird or more complicated if a train is traveling at some speed, let's say 20 miles an hour or whatever, and a passenger drops his cell phone from that person's perspective on the train, the phone that gets dropped travels in a straight line, straight down to the floor. But if you had somebody outside of the train on the ground standing still, watching the train go by, when they dropped the cell phone, it would appear to move in a parabolic line, not a straight line. And you would think, well, why parabolic, not like a diagonal line or whatever? But it's because as the phone falls, the velocity increases as it falls, because that's just kind of how gravity works. So that's why it would move in a parabolic line. So which is correct? What about somebody in space who would see the Earth rotating and orbiting in addition to the train's forward motion and the phone's falling motion? Which frame of reference is the correct or real one? All of them? None of them? They can't all be true at the same time. Either the phone moves in a straight line or a parabolic path. And this is where Isaac Newton's laws start to not work so great. Without an absolute frame of reference to measure against, we don't have any real way to measure anything. Everything is in motion: the Earth, the sun, galaxy, everything. There's no absolute frame of reference. Now, this is where they came up with the idea of ether, that there was some sort of...
What? You said ether.
Yeah.
Did you need me?
Some sort of ether filling the universe between the planets and the stars in the vacuum of space. It was actually some sort of ether that maybe is like a rarefied gas or something. Some kind of medium that can transmit light and gravity, just like air transmits sound waves. So when they used to think, and that light was moved in a wave-like pattern, and if you look at a wave on the ocean, or if you look at the way sound waves work, the molecules of water or air, they move forwards and backwards, but they end up in the same spot. So they're not really moving, they're just moving up and down, back and forth, or whichever. So they theorized that there was something like that out there in space that would do that to transmit light between the stars. Otherwise, if it was just a pure vacuum, how would light get from point A to point B without a medium through which it could travel? And there's a lot more to it. So what I'm doing, like the really, really short version of all this stuff, because I didn't want to have like a 5-hour episode, but any one of these topics you could obviously do many hours on, and I'm sure that people have in, physics lectures and stuff. The ether was theorized as a medium that could explain, Newtonian physics, that could help it work, essentially. So the ether could be in a state of absolute rest, and we could measure against it. It could be the glue that sort of held the strange universe together. If there was a universal reference point, the ether, then the velocity of light should change depending on how the Earth or anything moved in relation to it. Like for example, if you're moving towards a train and it's making noise, then that sound is going to change in velocity, and the frequency is going to become compressed, and it's going to go up in pitch. This is the Doppler effect. So something like that. That should also hold true for light. And it kind of does, but we won't get too much into that discussion because that kind of gets in the weeds a little bit. But in the 1880s, Albert Michelson and Edward Morley got up to some shenanigans. At the time, it was believed that light traveled in waves through the ether. Therefore, it should vibrate just like sound. And if there was this so-called ether, or the ether wind, then, let's say the Earth was moving through the ether, then you should be able to measure the difference in velocity of light depending on the direction versus the universal ether. So they built an interferometer that split a beam of light into two different paths, and they could change the length of one of the paths, and then they would rejoin those two paths. And this allowed them to actually measure the wavelength of light, but more importantly, the experiment proved that there was no ether. There was no universal medium through which light or gravity or anything else traveled. And this was kind of a big deal, and they kept doing experiments on this for a long time, because it's sort of a groundbreaking experiment. It changes the way that they viewed the universe. It would be like if you woke up tomorrow and all of a sudden oh, I guess we were wrong about there being a sun. It's actually something completely different than what we expected. We got to change our whole mindset on this. It's one of those kinds of a thing, even though it may not sound like that. But again, I'm doing the short version of, everything, including the interferometer experiment, which you can look up online. So a little bit after they determined that there was no absolute frame of reference or no ether, a guy named Lorentz figured out that the mass of a body increases with motion. When the velocity of the body equals the speed of light, its mass becomes infinite. And faster than light, the mass becomes imaginary, and there's no real way to represent that in the universe. It's just sort of a mathematical representation. You could put the equation in, but it doesn't make any sense. You familiar with Mr. Lorentz, Aging Ether?
Sure.
So he was sort of a predecessor of Einstein that led into the theory of relativity. But the basic takeaway is that if you want to lose weight, instead of going out there and running and moving around a lot and being all fast and athletic and stuff, actually you should become a couch potato, because moving makes you heavier. Thanks, physics.
Which ages you faster.
Yeah. Anyways,
I like it.
At this point, we're going to transition from Newtonian physics to relativity. It's kind of interesting just how hard it is for us to describe and understand our universe. Like you could say, yeah, sure, the planets are moving around up there, but it's very difficult to describe specifically how this is happening. And this is, all these theories that we're going over is just a very small amount of the work done throughout the years to understand our universe. So a young Mr. Einstein said, what if there is no such thing as an absolute frame of reference? And he assumed that all motion must be considered relative to something else rather than some absolute, such as the ether. In other words, there is no default state of rest. Anything can be considered in a state of rest. So let's get back to the trains. According to Einstein, it's okay to consider that the train is at rest and everything else, including other trains, trees, the galaxy, whatever, are moving in relation to the train. So this would be the frame of reference, or what they might say, a frame of reference from the perspective of the train. This seemingly simple assumption takes us in some pretty strange directions, and I don't have the time or knowledge to explore all of the implications of this, but this is one of the things that blows my mind is somebody comes up with an idea that if you were just having a conversation and somebody just said, well, what if instead of there being a universal frame of reference, we just consider a frame of reference from wherever, whatever reference we want can be at rest and everything else is moving in relation to that. You're like, okay, sure, whatever, who cares? But this takes us, this is completely revolutionary and pretty much supersedes like Newtonian physics. And it just sort of blows my mind how a little idea like this changes everything and leads to things like, the nuclear bomb and stuff like that. It's pretty crazy stuff. So old Steiny there figured out something else in addition to that, which is that the speed of light in a vacuum doesn't change. It's constant. And this is sort of another mind boggle here because it really should, right? Just think about it. Let's say you're playing a game of Flappy Bird on the train and you lose and rage quit by throwing your phone off the train in the direction it's moving. Then someone standing next to the tracks gets smacked in the face by the phone and also gets a free phone. The velocity that the phone smacks him in the face is the velocity that's thrown plus the velocity of the train. You can add those two velocities together, right? So it should also work like that for light, but it doesn't. What if light is thrown from the train? Or what if we consider the light from the screen of that phone as it's thrown? The light, even though the phone is thrown, still stays at the same velocity. It doesn't change, even though you might think that it should because you're adding velocity to the light or even subtracting. It just stays the same. It's kind of weird. It's a constant, and this is why we say the speed of light is a constant, even though I'm still kind of skeptical of this idea because it just doesn't make any damn sense to me. But whatever, I'm not like a smart person, so I'll take the smart people's words for it. One of the implications of this, I should say, is that it's not possible for anything to go faster than the speed of light, because when you add velocity to the speed of light, it doesn't increase in speed. It just stays the same. Kind of like a rev limiter on a car, I guess. I don't know. So how did he figure this out? Newton got his stroke of inspiration when an apple fell on his head. So I'm guessing that Einstein was walking next to some train tracks one day and somebody tossed out their cell phone and it smacked him in the noggin. And that's where he got his stroke of inspiration from.
Was it an iPhone?
Oh, it was. Of course it was. It was an iPhone. Somebody was playing Flappy Bird on an iPhone back in like 1914. Probably a little earlier. That's when he published, I think, in the 19 something. So let's say 1905, somebody on a train, a time traveler, threw out their phone because they rage quit the game. This game sucks. And then Einstein saw it coming and he considered the implications of a moving light source.
What is Flappy Bird?
Oh, you don't know Flappy Bird?
No.
It's a game that a lot of people find completely frustrating. So
what?
Is that like Angry Bird or something? Or?
I don't believe you.
It's kind of an older reference. I should have chosen something more current, but whatever. It's the first thing that came to mind.
Oh, you know what? I just got it confused. I thought it was Angry Birds. I was like, you don't know Angry Birds? I forgot Flappy Bird was the tap like helicopter game.
Yeah, that's that stupid cell phone game that everybody. There was like 2 weeks where literally everybody was playing it, and then it died a quick death. All right, but anyways, let's get back. So the part. Remember the part where we talked about velocity and mass, where mass increases with velocity. So according to Einstein, that's all relative. Let's take an example where you have two UFOs approaching Wright-Patterson Air Force Base from different directions. Let's also say that we just got abducted and are currently being probed on UFO number 1 or A or whichever.
Ooh.
So from our perspective, we are stationary and Wright-Patterson Air Force Base and the other UFO are moving towards us. The other UFO is moving so fast towards us, in fact, that its mass has increased quite a lot. You could say it looks like it stands to lose a little bit of weight. However, from the other UFO's frame of reference, they are stationary, they have not gained any weight, and in fact, we are the ones moving fast and in need of a diet. So wrap your head around that. Each UFO has gained weight, and at the same time, neither has, depending on the frame of reference. And this is, like I said earlier, this has all been tested. This is completely true. It sounds like science fiction and like it's made up and it's all bullshit, but nope, they have tested this and it's true. So depending on your frame of reference, it's such a strange thing. So to the poor soldiers on the ground, crapping their pants as they watch the UFOs fly over their bases, both UFOs have gained weight. But the totally bizarre takeaway is that reality itself depends on the frame of reference. Two or more different realities can and do exist simultaneously. All right, now let's get on to time. Just as mass and length change with velocity, time must also change. Look at it this way. Let's say that the UFO that we're on uses a novelty perpetual motion ball clicker thing to measure time. And being an alien device, it keeps clicking and never stops. So it's, like those desk things that go click, 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 whatever. They always run out, but this is an alien one, so it doesn't. So let's say at rest that it clicks once a second. As the velocity of the clicking thing increases relative to us, the clicking slows down. I can't really go into the math, but trust me, smarter people have, and this is what happens as a result of relativity. So as we observe time on the other UFO slowing down as its velocity increases relative to us, you'll see the clicker will also slow down. That's the device measuring the time. It could be a quartz watch or whatever. It doesn't have to be a clicker, but that's just sort of what I thought of.
Or an atomic clock might be better.
Yeah, an atomic clock. It doesn't matter what it is. Whatever we use to measure time will measure in slower and slower intervals from our frame of reference as we observe it, assuming we could observe it, because obviously at the speed of light, it's going to be very far away from us for a long time. So this is all hypothetical, but it has also been tested, like I said, so it's also true. Anyways, so if the velocity of the other UFO was 260,000 kilometers a second, time would be cut in half for the other UFO from our perspective. At the speed of light, time equals 0 or no time at all passes for the other UFO from our perspective. And let's just take a minute to think about that for a second. And there are some pretty strange implications that arise from that, but obviously we don't have time to go into them at all. So something going the speed of light, time stops completely. It equals 0. It doesn't slow down. It doesn't appear slower. It just stops completely. And that is weird. I just want to say that right now. That is a mind boggle. I don't like it one bit.
It was left by something.
Like, I find it hard to believe, but it's true. They've tested it. It's a real thing.
By design.
So the slowing down or adjustment of time with travel or with velocity is called time dilation. Now, let's say that we were a scientist working in a secret underground laboratory at Wright-Patterson Air Force Base, and we are abducted and probed by a UFO. While we are being probed, the UFO needs to run some errands around the galaxy so it travels away from Earth close to the speed of light. To an observer on Earth, time would slow down quite a lot on the UFO, but the same thing would happen on the UFO, and it would all work itself out in the end. To the UFO, time would appear to slow down on Earth, so the equation would kind of balance. But when the UFO finishes the probe or the errands or whatever and comes back to drop us off or the scientist off, that's when the magic happens. So the UFO has to turn around and come back. And because of this, because of its change in direction, it's not going in the same direction. The UFO and the Earth both experience non-uniform motion. So from both perspectives. So before we had time dilation on both ends that sort of works out. But this time, because it has to come back and return to the Earth, we don't have the same experience anymore. So time is no longer uniform on both ends of the equation. When the UFO gets back to Earth, less time has passed for the UFO. Let's say the poor abducted scientist experienced only an hour, while the Earth experienced a year. The scientist only aged an hour. In effect, from the Earth's frame of reference, he has traveled into the future. Okay, and that's pretty weird, but it kind of gets even weirder. One question that arises is that because of time dilation, wouldn't it be possible to travel faster than the speed of light? So for example, let's say that the UFO leaves at a high speed. Let's say just short of the speed of light, because as we covered earlier, if I remembered, I think I said that, did I say that mass becomes infinite? I don't think I said that actually.
I think you did.
I did? Okay. So as we covered earlier, you can't actually accelerate to the speed of light because mass becomes infinite, and that's not possible. But anyways, let's say that a UFO leaves at just under the speed of light, and it hops over to a star 10 light years away. At that speed, to the person abducted or whatever, the trip only takes 1 year, not 10. So that's faster than light, right? No, because I didn't mention yet, but from the frame of reference of the UFO, it's stationary, and the star and indeed the entire universe is moving around it, and the star is moving toward it. So part of this that I didn't mention is that this causes foreshortening in addition to all the other shenanigans. So as the velocity increases, the distance decreases. And I know it sounds weird, but that's actually a real thing as well. This whole thing is very strange. So from the UFO's perspective, the entire universe is foreshortened, and the UFO ends up going less than a light year. From the Earth's perspective, they go 10 light years at a speed close to the speed of light, and it takes them slightly longer than 10 years. The UFO would not travel faster than the speed of light from any frame of reference, even though it might seem like that should be possible. It just depends on where you're observing from. But it doesn't, even though from the UFO's perspective, it takes less than a year to go 10 light years. Kind of weird, right? It's kind of hard to wrap your head around this stuff. But anyways, if the UFO was racing a laser beam to the star, it would lose to the laser beam, even though the distance is 10 light years, and they cross the distance in less than a year. From the light beam's perspective, traveling at the speed of light and not slower, time equals 0, and the light would get there instantly from its own frame of reference. It would be instantaneously, the moment it left, it would instantaneously arrive at the star 10 light years away. So from the Earth's perspective, the UFO would take a little longer than 10 years to travel because it's traveling slightly slower than the speed of light. And from the Earth's perspective, the light would take exactly 10 years to get there. But from the UFO's perspective, it takes a little less than a year. And from the light's perspective, it's instantaneous. So this doesn't mean that from the light's perspective that it's traveling faster than the speed of light. Rather, the universe's thickness is foreshortened to 0, and thus, it traveling any distance anywhere in the universe is instantaneous at the speed of light.
Man, I don't know what you just said, but it sounded smart as fuck.
It's crazy. Stuff is just absolutely bananas. But
that's 300 meters per second. Believe it. 1,000,000 miles faster than sound.
It's been tested though. Like this stuff has been tested, and it's apparently true. It's just absolutely bananas though. Absolutely bananas, man. Let's go back to Newtonian physics, like inertia and all that stuff. I can wrap my head around inertia. Like there's chores to do and your wife wants to kick you off the couch, but there's too much inertia, so you can't actually make it off the couch. I can wrap my head around that. All this light speed nonsense, going anywhere in the universe instantaneously, it's too much for me, for my poor little tiny brain.
That's an unstoppable force meeting an immovable object.
Yeah.
A couch potato.
But this is kind of crazy. So according to the general theory of relativity, time and space are not fixed, but malleable, depending on the frame of reference. It's so bizarre. So this is the understanding of the universe according to Einstein, but that probably isn't the whole story. I mean, there's so much more for future generations to discover, and it's kind of exciting. And it just sort of, makes me think that just as crossing the ocean once was an insurmountable obstacle, but it's now trivial, maybe someday with new science and understanding and technology, the vast distances between the stars will no longer be obstacles, but will be trivial to travel. Just like today, hopping on an airplane and flying to Europe, no big deal. But anyways, the theory of relativity has been tested and tested to death, and it seems to pass so far. So we can travel forward in time compared to a certain frame of reference. And that was maybe a really long-winded way of saying, I mentioned it on a previous episode, but I wanted to go a little more depth into it because it's just so damn fascinating. Like, we can do this. This is actual science fact. If we had a machine that could travel, any percentage of, like, let's say even 10% the speed of light, then we could definitely travel in time versus Earth, let's say our starting point. And it's just pretty cool. So I think I got that approximately correct. Was that somewhere in the ballpark, Agent Ether?
Yeah, I think so. It touched on all the basics. I certainly remember from going to college 25 years ago. Yeah, Agent Anderson's like, you can do this, right? And I was like, I don't know. It was so long ago. But it is really important because you can't talk about time travel using speed or gravity or light, wormholes, black holes. You can't talk about that kind of stuff unless you have a basic understanding of special relativity and how light works.
And I would just like to remind everybody or just mention that I forget the exact date, but it was somewhere around 1914 or 1916 or somewhere in the 1910s that Einstein actually published his theory of general relativity. And that was a long time ago, guys. So he was pretty much ahead of the curve there on that one. And we're still making discoveries based on his theories, like gravitational waves and stuff, which were not that long ago.
Hey, you know what? When his brain was, when he died and his brain was removed, he had an abnormal brain. And again, I plan to talk about this later. Is like, what if he was able to talk to his past self? What if he himself is an agent of time travel?
There's actually some shenanigans involving his brains, but like some.
That's all diced up and it's in formaldehyde.
Somebody actually had his brain for a while, and we won't get into that though. That's a whole other topic, Einstein's brain. But anyway, so let's move along to Agent ETA. What do you got for us, ETA?
Oh boy. All right. So imagine, if you will, a big chunk of time missing out of our modern history. Something that was potentially fabricated, if true. what I'm talking about is the hypothesis of the phantom time, or to be, more precise, the phantom time hypothesis.
Sounds like a
Whatever,
Star
dude.
Wars
Anyways,
movie.
So, yeah, it does, doesn't it? I like the sound of that. Yeah, dude. So, all right. So, this paper is what it's based off of a paper written by a German historian named Herbert Illig. And he published this paper originally in 1991 and then republished it in 1994. So, I'll give you the long story short, the short and curlies of it basically is between 1614 and 19 AD. The Catholic Church basically kind of rewrote history. And so what they did, there was three main people involved in this. And what the paper claims is that the conspiracy to do this, to change history and to change like the timeline in that time, was brought together by the Byzantine Emperor Constantine VII, the Holy Roman Emperor Otto III, and the Catholic Pope Sylvester II. And I don't know why, but Sylvester just sounds like a sly motherfucker if I ever heard of a pope. You know what I mean?
The slyest.
Yeah, I don't know why, but he sounds pretty damn sly, So at any rate, the paper basically says that they conspired to change history, to make it to where Otto III, the Holy Roman Emperor, started his reign at 1,000 years, 1,000 AD. And so that would line up with like the new like reign, you know what I mean? The new Christian millennium, And so what that means is that basically there's 297 years of made up history that they fabricated and added on to the record to fit their goals for the most part, And I don't know. It's highly contested that this is either a thing or it's not. But I actually kind of think that I wouldn't be surprised if other rulers throughout the world, throughout different points in time, had done similar things just to suit their needs. You know what I mean? I wouldn't be surprised at all. Like, I'm okay with the idea that, like, say, for instance, like, we think it's 2022 right now. Well, possibly it actually might not be. But I mean, that just depends on what you, what timeline you want to abide by. But who knows what freaking year we're in? You know what I mean?
There's choice, man.
Yeah, I mean, the world was supposed to end in 2012 and it didn't. So obviously somebody got their numbers crossed somewhere.
No, you're wrong. It was 2000. We were supposed to die way back in 2000. Y2K, baby.
Mm-hmm.
All right, Agent Ether. So you have some other stuff. What do you got for us?
Well, I want to talk about general relativity and special relativity as it relates to some time travel, specifically as it relates to time travel through gravity, through string theory, and that sort of thing.
Oh, boy. Let's hear it.
All right. Well, we've talked about, the basic relativity equation E equals mc squared. But that's really very simple. It's a simple version mathematically and conceptually. It has much larger implications. The fact that the velocity of light is always a constant means a lot of physics equations get interesting solutions that are different from Newtonian physics. The difference between special relativity and general relativity is that general relates to gravity and acceleration, while special relativity relates to speed and time. So you get these sets of equations that are made to model the real world of physics.
Okay, so I could use those equations to, let's say, describe how my car is moving down the road.
That's Newtonian physics. So more how your car is moving very quickly down the road and how that relates to space and time.
So we're talking about stuff moving very quickly then?
Yeah, stuff moving very, very quickly. It's hard to conceptualize because we're talking about mathematically advanced ideas, but it's possible to understand the basics. All right, so for my first example, I want to look at an interesting case that relates to time travel, specifically an infinite or Tipler cylinder. It's not something that anybody has observed. It's something that's been predicted. It's a mathematical solution to Einstein's equation, so it makes it something that's possible but we don't have any way of detecting it or proving it right now.
So it's just theoretical.
Yeah, a lot of this is theoretical. I mean, really, all of it's theoretical when you're talking about time travel as it relates to things like wormholes, cosmic strings, and infinite cylinders.
Oh, right. Yeah. So we do have relativistic time travel to the future has been proven.
Well, you could say we're all moving towards the future at a rate of 1 second per second.
I guess you could. But what I mean is, we don't have the technology to build such a device. But like I mentioned earlier, if we had something that could travel even just 20% the speed of light, then we would age slowly compared to a frame of reference, let's say on Earth. So we would, in effect, be traveling into the future from Earth's frame of reference.
Well, you do get astronauts who are different ages, the ones that go into space, and that kind of relates to what you're talking about. The idea behind the infinite cylinder is to take a lot of matter, like 10 times the mass of the sun, you stretch it out into a very long cylinder, and Hawking argues this would have to be an infinite cylinder with negative energy. You rotate it along its longitudinal axis at billions of revolutions per minute, and if you accelerate a craft properly, it could travel back in time.
All right, well, now we're just getting silly.
No, I'm going to explain how and why this works. So the cylinder creates a frame dragging effect, and this is predicted by general relativity, where rotation influenced the mass near it, dragging along space and time close by. So you can think about kind of twisting a Chinese finger trap into the surface of a balloon, and that's kind of how it's warping space-time. You can imagine it traveling really, really fast. And this creates a closed time-like curve, or CTC, which we've actually discussed in other episodes, a world line that closes back on itself, returning that space-time to its starting point. And CTCs are mathematical solutions to general relativity, and they pop up everywhere. They can be found when solving equations relating to wormholes as well, which Agent Anderson is going to discuss in a bit.
Yes, I am.
So if we could somehow manipulate space and time and control negative energy to create this infinite cylinder, we could have a ship traveling along in a spiral along this closed time-like curve, and it could pop in and out at different points in time, future or past. Now, we can keep going down this rabbit hole. We can keep asking, what does this mean? How do you build a ship? How fast is it going to go? How will this affect people on the ship if they're in this CTC? And really, it never ends when you start thinking and conceptualizing what's going on. So I'll just give you one last definition, and that would be negative energy. It takes positive energy to separate matter. So maybe gravity is using negative energy to pull them back together.
So gravity is a form of negative energy?
It is. Some may argue, some physicists argue, that gravity could be considered a form of negative energy.
Okay. Now, am I correct in saying that they haven't really figured out what gravity is?
Yeah, gravity is one of the tough ones, although I think recently they detected gravitational waves, so that was kind of cool.
Yeah, but a gravitational wave is not the same thing as like a gravitron or whatever.
A particle of gravity.
I think that's a ride at the fair. Gravitron is graviton, I think is.
No, it's not the same thing. But in general, we can use gravity to time travel, maybe, if we manipulate it to warp space-time in some way. So here's an interesting thought experiment. If you're having trouble grasping it, or if you just want to think some more about it, as you get close to the center of the Earth, the strength of gravity increases. So time actually runs slower for your feet than it does for your head. And this effect has been measured by setting 2 atomic clocks on different shelves. The lower one will start to slow down.
Wow, that's why my feet look so good.
So to travel to the future, you could just look for an area that has really strong gravity, take your advanced technology, really advanced, Remember that gravity is just where space-time is bending. So anything that happens affects space and time, and gravity is pulling on both. And what I'm talking about here would be a one-way ticket. But remember, you also have to travel really, really fast, close to the speed of light. And those effects are time dilations, the difference in time measured by 2 clocks, usually because of effects due to velocity when you're traveling at high speeds.
So you're saying that gravity is a part of that, but what if you had something like a black hole with massive gravity? I'll get to that later.
Yeah, that's definitely along those same lines. So I have one last time traveling possibility to discuss, and this one was new for me, so I was kind of excited. It relates to string theory. Now, string theory is kind of out of vogue. I don't know if you guys watched Big Bang, but even Sheldon's like, oh, this string theory, am I wasting my time? String theory only works if space-time has 10 dimensions. It involves particles that haven't been discovered yet. Strings are smaller than quarks, and quarks make up all matter. String theory says quarks are not the smallest particle. Instead, quarks are made of smaller vibrating strings. If true, it might unite into a singular framework to explain general relativity and quantum mechanics.
Ooh.
So knowing this, we can talk about cosmic strings. Now, cosmic strings stretch across long distances and affect gravity. They are one-dimensional tubes of energy stretching across a length of the universe, and they're predicted to have huge amounts of mass. So you can either make them infinite or loop them, and 2 of them close together could bend space-time so much that potentially you could control it and time travel. An object to the string travels at high speeds and uses time dilation to travel through time.
Okay. Kind of like a wormhole.
Kind of like a wormhole.
Well, crap. Now what am I going to talk about?
No, it really is not the same as a wormhole, though, because in this case, you're bending space-time so much, it's almost like a light cone where light can be bent in 2 directions. And because you can warp the light in 2 directions, you can kind of create a shortcut, and you would be traveling faster than the speed of light. And that's different than a wormhole.
Right. So if you're traveling faster than the speed of light, you actually go backwards in time.
So that's what I have over here for different types of time travel / time machines.
All right. Well, I'll get into a little bit of some more physics stuff. That was one of the really cool things about this topic, is that it's not like all make-believe. We're not just sort of theorizing here saying, well, perhaps this or maybe that. This is actual science. Like, not all of it has been proven, but it's really exciting to me because some of it has been proven. And we are talking about something that is, scientists come up with this stuff. It's not, just a couple of weirdos with microphones talking about in their living room, We're talking.
No, that would be us.
Yeah, that would be us. We're talking about real professionals here, and that makes it really exciting for me. All right, so let's talk about black holes and wormholes. A black hole is created when a big star collapses. It keeps falling in on itself until all of its matter is compressed into a single point, the singularity. Surrounding this is what's known as the event horizon. Now, contrary to popular belief, this is not actually the surface of the black hole, but it's the point at which nothing can escape, including light. So maybe it's a surface, maybe it's not, we don't know. There are many theories about it, but we know that light cannot escape. And what's inside? We don't know for sure, but they think there's a singularity in there.
Oh, there's all kinds of interesting theories that don't even relate to time travel about black holes, but it's very physics intense.
It is. I read up on some of that stuff and I didn't really understand any of it, and I figured if it didn't make sense to me, what's the point in talking about it? Besides, has nothing to do with time travel, really. There's lots of different theories you can talk about for black holes, but let's get into the time travel aspect. So if black holes exist as theorized, it opens up some interesting possibilities. For example, it would be possible to travel into the future. According to the theory of relativity, if one got close to a black hole but did not cross the event horizon.
This reminds me of that movie. What movie were we watching where they landed on a planet and it was a tidal planet near a black hole? And
Interstellar.
yeah, and 7 years passed there while
Yeah.
whatever time, minutes passed there while 7 years passed on Earth.
The one problem I had with that movie is that, now I'm not a physicist, I don't know for sure, but I imagine that if gravity was strong enough to cause that kind of time dilation, it would actually be closer to like a neutron star than a planet. And anything getting anywhere near it would just be, pulled apart by tidal forces.
Oh, well, who knows? All that whole movie got kind of weird really fast. So.
Yeah, it was fun. A lot of people liked it. I was sort of like, wait a minute. Wait just a minute here.
But, that has, if you think about it, a closed time-like curve where events along the curve have been affecting themselves.
Right.
So it's like a loop. So that's interesting.
Yeah, it's sort of like the 12 Monkeys version of time travel where you can't actually change anything. It's already happened. So you're just sort of, whatever your frame of reference is, like if you go back in time, that's your frame of reference. You can't change what happens in the future because what you just went back to did has already happened in that future.
Yes.
Even though for you it hasn't yet. So it's sort of like that.
Definitely solves the paradox problems.
Right. All right. So anyways, the extreme gravitational forces near a black hole would make time pass slower for somebody near the event horizon compared to somebody far away. So as Agent Ether was talking about earlier, the gravity itself bends space-time. And theoretically, if you could somehow get a ship close to the event horizon, but not go in, then you could slow down time for yourself compared to, let's say, on Earth.
Sounds like it's a one-way trip.
Yeah, it is. From what I read anyways. I don't know. That's what it said on Wikipedia, man. No, I had to look at some other sources too. Not just Wikipedia. I didn't just look at Wikipedia. Gosh. But what if one accidentally or purposefully went into a black hole? I mean, I wouldn't do it. Lots of people would not do it, but I guarantee you there's somebody out there, given the opportunity, would jump right into that damn thing, right? There are, those daredevil skateboarding types, maybe? I don't know. They're out there, though.
Hey, somebody has to do it.
Yeah. So what would happen if you fell into the event horizon? Well, you would never actually enter the black hole. In fact, nothing can, at least from your frame of reference, or from an outside frame of reference, I mean. Because when you hit the event horizon, then time equals 0. At least that's the way the math works out.
That's the way the math works, yeah.
From an external frame of reference, right? So not from the person falling in, not from their frame of reference, but from somebody outside, they would never actually see you fall into the event horizon, theoretically. Now, obviously, we've never tested this, and obviously stuff has fallen into black holes. We know that that's probably a thing. So it's sort of one of these contradictions that, like I said earlier, when you make a couple of just really simple adjustments in the way you look at the universe, relativity versus Newtonian physics, those have all kinds of implications that you wouldn't think ahead of time. Like it leads you in all these different strange directions. It's really cool and also really confusing. I like my Newtonian physics. Thank you. I just really prefer that stuff. You got a sled on ice, you push the sled, it goes for a certain distance until friction slows it down, the end. I like that. I can wrap my head around that.
Unless the sled's traveling really, really fast, then you have problems. Well,
I mean, yeah, but in real life, you're never going to see a sled going, 10% of the speed of light or something. That would be silly. What kind of sled are you on anyways? Cut a hole right through the earth. Okay, where was I? So black holes allow a different type of time travel. A specific type of black hole could be used as a wormhole by bending space-time between two distant points. Now, there's actually a couple of different ones like this. Agent Ether talked about one sort of like if a black hole was in the shape of a cylinder. I think that relates sort of to like what you were saying. But if it was able to not collapse into itself using like negative mass or negative energy, then they could make it a stable wormhole. So she already covered that one a little bit. But a classical wormhole, or sometimes called an Einstein-Rosen bridge, might connect not just two distant places, but actually two different universes. And it might do this by bending space-time. So besides different universes or two different places, the two ends of a wormhole could lead to different times. So that's also another possibility. Such a wormhole could lead you to some specific location, but forwards or backwards in time. So how would a wormhole actually work? Imagine the universe is a 2D plane. The wormhole would be a 3D tube connecting 2 points on that plane. So in other words, it would sort of require a fourth spatial dimension. But the scientists have proposed that this is actually possible. And like we said earlier, it's theoretical. But the math works out for some of these, for all of them really. But there's many different types of wormholes that are possible. But one idea is that some sort of exotic matter, such as matter with a negative mass, would be needed to create the wormhole in order for it to be stable so you could go through it. Others physicists proposed that an electrically charged fermionic matter could make a tiny wormhole. Now, I have no idea what any of that is, but it's apparently possible, so I just throw it out there. You guys have fun figuring that one out. Agent Ether, do you know what a electrically charged fermionic matter is?
It has been a long time since I got my physics degree, so I'm just going to say no.
Okay, fair enough. So the Einstein-Rosen bridge version of a wormhole would require a white hole, an object that is actually the exact opposite of a black hole, and that is that nothing can actually go in, but stuff can only come out. And it would also have an event horizon, by the way, and that the event horizon would be the point at which nothing can enter, but stuff can only exit. White hole, it's only theoretical at this point. No one has ever been observed. No one's ever found one. It's just theoretical, but they say it's possible, even though we have never found one. Except maybe the Big Bang. Some people think that might be sort of like a wormhole, and there are theories that there could be something similar to a Big Bang going on inside of a black hole. So that's a kind of an interesting theory. Of course, a one-way trip isn't really ideal, and this is why the traversable wormhole, and this is why the traversable wormhole, or one that allows travel in both directions, is really what scientists get excited about. It's been observed that energy density can be negative relative to the vacuum of space. And I think they call this the Casimir effect or something.
Cashmere effect. Cashmere, like a sweater.
Is it cashmere? Okay.
It is not cashmere.
I thought it was Casimir.
It is.
Okay, Casimir. Good. I was like, man, I must be losing my marbles, misremembering something like that. Okay, so such negative density could be used to form wormholes. It's possible that a negative mass cosmic string created during... Oh, wait, you already talked about that. So I'll skip that one. Stealing my material.
We had to go back and forth. We're doing good.
We are doing good, actually, yeah. The catch to all this wormhole and time travel stuff is that the time travel aspect is subject to relativity. So one could not travel back in time before the creation of the wormhole. And, one of the problems we've discussed a little bit is causality. So, for example, one idea is that you could have one end of the wormhole moving close to the speed of light and another end of the wormhole stationary. So as the one moving close to the speed of light gets further and further away, you would actually travel in time if you went through the wormhole and got out the other end. But no matter which end you went through, you would never be able to go back in time further than when the wormhole was created in the first place. And that's what I mean when I say that it's subject to relativity, or the theory of relativity. So that's why, you could use it to go forward. You could even use it to go back in time, but there would be a limit to how far back you could go. All right, now if something was able to travel faster than the speed of light, then this would also allow time travel. Because let's say you're looking at like a flashlight or a radio signal or some kind of signal being sent, right? If that signal traveled faster than the speed of light, then it would reach its destination before it left from where it started. Because that's just how the theory works out. Like, what? I don't know. I don't know how that makes sense, but apparently, theoretically, that's what happens. Obviously, they've never been able to test this because, as far as I'm aware, scientists have never been able to make something go faster than the speed of light. But if it left and it traveled somehow faster than the speed of light, whatever we're talking about, whether it's light or a ship or whatever, it would arrive at its destination before it left from all frames of reference. And that's the important part, because when you're talking about relativity, like with time travel, like if you're talking about just going in a straight line without some sort of reverse trip, the frame of reference, it's only from that frame of reference and not from all frames of reference. So it's kind of like, well, have you really traveled in time? It's if a forest falls in the tree kind of a deal, right? But in this case, it would be from all frames of reference. So have any evil scientists managed faster than light travel?
Well, they've slowed light down
One would hope
a
not.
lot.
I saw that.
Always in the news. They're just making it go slower and slower.
It's so cool.
Yeah.
I thought light was a constant. How can they do that?
Well, it's a constant in a vacuum.
Oh, in a vacuum. Okay, that's the important part there. I left out that half of the sentence. All right. So a dude named Gunter Nimtz and Alphonse Stahlhofen of the University of Koblenz claimed that they sent photons instantaneously between two prisms about 3 feet apart. But as of this recording, the results of this experiment are disputed. So they say that they did it. A lot of other scientists are kind of like, no, you didn't. We don't believe you. And I guess only time will tell to see if other laboratories if other laboratories can replicate that particular experiment. So that's pretty much the only thing I saw where somebody may have done something faster than light, but there's nothing other than that. No, it has not happened yet. And if it had happened, then it would have already happened because it would happen before it happened.
So confusing.
I know, right? Doesn't make any sense. The last thing I found that is sort of related to time travel is MIT held a time traveler convention. I forget. I didn't write down the year. It was like 2005 or something, right? They had a time traveler convention complete with a DeLorean and a landing pad, but alas, no time travelers from the future came. Or at least not that we know about. Okay, so that's all we had this week for time travel. I mean, it's one of those topics where I feel like we could just ramble incoherently about it on and on because it's so interesting. And it's, some of these theories have been proven to be a fact, while others are hypothetical, even though the math works out. But it's still just a really, really fascinating topic that I kind of enjoyed.
Yeah, lots of fun. And big shout out to all of our listeners. There was a lot of requests for this topic.
Yeah, thanks for requesting this, you guys. Usually I'll just, name the one person that requested it, but in this case, there were several. So, we don't have time to name all of you because we're lazy and we don't want to look it up, I guess. All right. Thanks for listening.
Keep it strange.